I would like to invite TSZ Nam Chan. He will speak about SLAM, efficient sweep line algorithm for kernel density visualization.
Today, I will present this topic, SLAM efficient sweep line algorithms for kernel density visualizations. And I think you have already introduced me, and I'm from Shenzhen Universities. You can just call me Edison. So why do we need to consider kernel density visualization, KDV? So you can see that, all right. Let's see this one. So you can see that these kernel density visualizations can generate this kind of heat map. So you can see that if we use the red or the orange here or the red here, denote the hotspot of the COVID-19 cases. That's a very high density region. So we will use the red color to color it. If the density is very low, then we will use maybe this kind of yellow color to color it to indicate that this is not a very serious. And we can also use this kernel density visualizations for visualizing the hotspots of crime events in a region. For example, you can see here this red region, right? So this denotes the very high density region in this park. All right, and then for other parts, if the density is not that high, then we will use the green color to color it. All right, so this can be used in both COVID-19 hotspot detection, or maybe you can say that is disease outbreak detection, or the crime hotspot detection here. And then you will say, okay, kernel density visualization. Then what is kernel density visualization, KDV? So I will use this crime rate prediction as an example to illustrate this concept. So we can see that there are so many black dots here. Then each black dot represents the location of a crime. For example, it can be a robbery, commercial burglary, or motor vehicle thefts. So we need to predict the crime rate of a location Q by computing the kernel density function FPQ. And FPQ is stated here. So you can see that, okay, this is the kernel density function, right? And this is P. P is the data set. And you put the Q, you put the pixel, or the location here. And based on this equation, then if this density is very high, then we use the red color to color it. If this value is quite small, then we use the green color to color it. And this equation, you can see, is based on the Euclidean distance, and it is based on the bandwidth parameter. And this bandwidth can somehow control the smoothness of the visualization, right? However, KDV is very slow. The time complexity of computing KDV is OXYN, where X times Y is the resolution size, and N denotes the number of data points. That's mean the black data points here. And you may say that, okay, XYN is not that high, right? And maybe let's say if X times Y, you use the resolution size of 1280 times 960. I think it's pretty normal nowadays. And N, we use maybe 1 million data points. That we have 1 million data points and multiply 1280 times 960. It's a very, very high. This number is very, very high, right? And also, domain express need to generate multiple KDVs, but not one KDV. They generate multiple of them. Maybe they do this kind of bandwidth selection. That's been tuning this bandwidth parameter, and you can visualize different. You can have different visualizations, and you can zoom in. I want to zoom into one region, or you can use some panning operation. I want to see the hotspot in different regions, right? And then I can do some zoom out operations, and we can also do some filtering and other kinds of applications. That means domain experts need to generate multiple KDVs. And you know that generating only a single KDV is already very, very slow, right? Let alone to generate multiple KDVs. So that's why there's so many complaints from the literature. For example, you can see the total runtime of density estimation quadratic in the exercise, and also you can see that, okay, the practical algorithm, and this is the KDE is very time consuming, and quadratic computational complexity being a commonplace. So this is very, very slow. That's why in existing work, some existing one of the existing solution is that we can use the range query based solution. What is the meaning of this range query based solution? You can see that for pixel here, you can see this pixel, the Q here, we only to count all data points that are within the distance B, right? That's this memory parameter B. So that means we can only need to find this range first. After I find this range and all data points here, we can substitute this range query set into this equation, and then we can remove this zero, right? So there's so many tree structures, the indexing structures can be used. Those indexing can be used to improve the practical efficiency, and this solution is quite simple. However, this approach cannot reduce the worst case time complexity. You can imagine that this B, let's say this B, is very big, which covers the whole region. Then this RQ will become this P, right? That means you still need to scan all those data points. So that means the time complexity remains in O, X, Y, N, right? So in our contributions, the SLAM approach, this method is the first, this is the first word for generating a single KDV that can reduce the worst case time complexity. For example, this is OXYN, right? And this is one approach is OY times X%. This is reduced. You can see the time complexity is reduced and the space complexity is the same. And this solution generates the exact KDV. That's mean no approximation, no loss. That means the visualization is exactly the same as the original one. And in practice, this approach can achieve 1 to 2 order magnitude speedups for generating KDV using large-scale datasets. So let me present 2 core ideas of them. The first core idea is that you can see that if we consider 2 consecutive pixels here, and 2 consecutive pixels can share many data points. For example, you can see that, okay, this is a range query set, and this is another range query set for the consecutive pixels. They can share a lot of right data points or these right circles here. So the first question is that, can we share computations between 2 consecutive pixels? This is the first core idea. And the second core idea is that this FPQ, if you substitute this RQ into this equation, you can decompose this equation, which is based on some linear algebra operation. You can decompose this Euclidean distance, right? So you can decompose it into this form. And that means if you can maintain this RQ, this ARQ, and also this SRQ in a very efficient way, you can also efficiently evaluate this one. So that's why another question is that how to efficiently maintain this manual RQ, ARQ, and SRQ. So now let's consider, okay, we have this core idea, right? So let me consider the details. So let's consider a row of pixels. That means the Y coordinate is exactly the same as for all those pixels in a row. And you can see that those range query sets, they are covered by this envelope, right? And this envelope can be defined in this way. So you can use ON to find this envelope because you just scan all those data points and check whether the K minus, that means the Y coordinate here, minus P dot Y is within this bandwidth B. That means this is B and this is B, and this includes all those data points here, right? So after I have this set EK, then we can have this lower upper bound concepts. So let's say we consider all the blue data points here, and you know that those data points, they're within the region, the range B. So we can somehow decompose it because this is Euclidean distance. You just decompose it in this way, and then this Q, you can see that if distance QP smaller than B, and Q dot X must be within this range, this lower bound, and also this upper bound, right? So let's say we can just let this LBKP and UBKP into this P, that means P dot X minus this one, and P dot X plus this one. So we have this, that's it for each data point. We try to maintain this value and this value. And you may say that, okay, P4 is not within the circle, right? So if P4 does not within the circle, then this inequality does not hold. That's mean the lower bound may not be in this that means may not be within may not fulfill this sorry, they should not fulfill this inequality. All right. So you may say that, okay, there's a square root here. This value is this a value? Is this an imaginary number? You know, this is, if it's more than 0, that's an imaginary number. The answer is no, because all those data points within this envelope, they must fulfill this they must fulfill this inequality. That means this one must be bigger than 0 based on this. So that means we can maintain all the lower bound, lower bound, upper bound, lower bound, upper bound, lower bound, and lower bound, upper bound here. And then we can convert this range search problem to the interval snapping problem. All right. So all those data points, if all those data points are within the circle, then you know that this inequality holds. Then that means the LB and UB that means Q dot X is within. That means this Q dot is within this range, right? And this, if P dot P4 is outside this circle, then this must not, this inequality must not be fulfilled. So this is outside, right? So that means we can convert this problem to another problem, and then we can use the split line algorithms to solve this. The core idea is that we try to sort the coordinates of the endpoints of all intervals. So okay, that's it. Maintain an order. And it takes O(n) not n in the worst case, and not n time in the worst case, and use the split line L to process these three terms. Why do we need to consider these three terms? Because these three terms, they're exactly this one, this term, and this term. This is based on the core idea too. So we try to process these three terms, and then we use these three terms to calculate APQ. And the time, because we just do some swip line, that's why you maintain the swip line and scan. Then the time complexity is OX plus n. And you know that we only consider one row of pixels. So we have Y rows of pixels, right? So the time complexity is OY times X plus n not n. And this is the slam shot. And we have another approach which is called bucket-based split line algorithm, and it can further remove the sorting step. And for details, I have one paper for discussing this, and you can refer to that paper. And if we reduce if we remove that sorting step, the n not n is also removed. So the slam bucket takes OY times X plus n time. And these are experimental results, and we have used 4 large-scale data sets and location data sets for testing crime event, traffic accidents, we run course, and you can see that by varying the resolution size, our method, this is the best method, slam bucket route, is the best. You can see that it achieves. For this one, it can achieve a visible split up compared with the existing. That's been set order, all of them. They are the existing solution. It can achieve a visible split up. So this is the ongoing work and also future opportunities. So first, we want to develop the new software package Live KDV based on our first techniques and extend SLAM to all kernel functions, because we only focus on some particular types of kernel. Now we consider the Gaussian kernel and also some exponential kernel, and also we further develop the optimal solution, because you know that the lower bound for generating KDV is, because at least we need to process all those pixels and access all those data points. So in the lower bound time compressed is omega xy plus n, but our current upper bound is oy times x plus n. That's why either we have a gap in between. Either we can increase this lower bound, and also, or we can reduce this upper bound. And we want to support other types of KDV, for example, network kernel density visualization, NKDV, and spatial temporal kernel density visualization, STKDV. So this is the end of my presentation. If you have any question, you can ask me. All right. Hello?
Are you hear me? Okay, thank you, Edison. Very expressive your presentation, very energy and very important applications. For example, I see on first diagram COVID situation. We have some research also in this direction. First of all, I try to ask you send me your presentation for sharing with our colleagues, and we would like to use your methods because it's very impressive. Thank you, congrats. Very good. Maybe someone have a questions, remark. I think this situation can be applied in our research center. We can discuss further because we also need to imply these applications in our urban system, because we will analyze some processes. Yes, it's very interesting. And I hope on next our conference you make a new report.
Yeah.
And we wait you. Yes, of course. Maybe you have some conference paper about this direction, and you can share with me, and we add and works of conference your work. Okay? Can you make some paper, conference paper for us? Very impressive. Thank you. Goodbye.
Bye.
Okay, next speaker. Now I would like to invite Professor SUAT, University China, Qiaoqiao Zhou, Generalized Group Testing. Please.
Okay, thanks for having me. So it's a good pleasure to present my work. So I'm Qiaoqiao Zhou from Shenzhen University of Science, Shenzhen University of Advanced Technology. So today I'm going to talk about generalized group testing. It is a topic about how to estimate structure signals with fewer potentially nonlinear measurements. So this is a joint work with our undergraduate student Shiwei Chen from Chinese University of Hong Kong and Siddharth Jaggi from University of Bristol. So let me briefly introduce what is group testing. So it is a topic which was introduced in, during World War II. At that time, a large amount of soldiers they have to enter the army, right? So huge, there are a large amount of people. So a subset of them get infected. So, but the identity of this subset is unknown a priori. So our goal is to find out this subset. I mean, find out the infected people. So a simple and naive strategy is to test them one by one, right? However, usually the number of infected people are much smaller than the whole people. For instance, maybe they are in a sublinear region. Sublinear region. So this essentially says that this is a sparse problem. So there should be some sparsity we can leverage to efficiently solve this problem. So Dolphin, he proposed the group testing idea. So instead of testing them one by one, we can put samples of different people together. For instance, I can put samples from these 2 persons into a single test. I can put samples of these 3 people into a single test. So the test outcome will be positive if at least one of the Can you hear me? Hello?
We hear you. Tech problems, I think. Yes, you can continue. Right now, we will share with your presentation because we did not see right now.
Can you see me now?
Please wait 1 minute. Yeah, share with your presentation. We did not see. No, just a minute. Oh, no, we don't see.
Okay, let me do this. Can you see now?
Yeah, we see right now. We can
Okay.
continue. Skip slides. Yes.
So again, the test will be positive if it at least contain one infected person. It will be negative if all of the people involved are healthy. So we want to construct a series of this kind of group tests in order to infect in order to infect the subset of infected people. So a very long previous result is a lower bound. So suppose you're allowed to make an up to small error. So the lower bound, this means the number of minimum tests you have to use to identify the infected people is always D log N over D. So depending on there are two kinds of strategies. One is called adaptive strategies. Another one is called non-adaptive strategies. For adaptive strategies, you can always use your test result of your previous test result to design your next test design. For instance, you can use a two-stage group testing scheme. So first, you test 5 people. If all of them are healthy, if the test result is negative, this means all of them are healthy, right? So if the test result is positive, then you can test them one by one. So this is adaptive strategies. So for adaptive strategies, the well-known binary splitting algorithm already achieves the lower bound. For the non-adaptive, it is unknown until 2020. So this group, they resolve the best number of tests. Now, in our previous test design, we make an assumption. What is the assumption? The assumption is the test result is positive whenever there is at least one infected person. But in reality, this requires your test kit to be very sensitive, or sometimes there will be noise to affect the test result. So what does this mean? This means if your test result is not sensitive, or if there are some noise, even if you have some infected person, your test result may still be negative, right? So in order to handle this kind of scenario, different people have proposed different kind of test model. So in order to introduce them, let me first introduce the notion of test function. So what is test function? So test function is a mapping from the number of infected person to the value between 0 and 1. So the input to the test function is the number of defectives in a given test. The value of this function is the probability that the given test being positive. So for the classical group testing, our test function is our step function, right? So because we say that in the classical group testing, so the test result is positive as long as there is at least one defective person. So another model is special group testing. So for instance, you have a special group testing with 5. So if you have more than 5 people, your test result will be positive. If you have less than 5 people, your test result will be negative. Another one is called stochastic special group testing. So in this case, you have 2 parameters, L and U. So if the number of infected person in your test is less than L, it will always be negative. If your number of defective person is larger than U, you will always be positive. If the number of defective person in your test is between these 2 values, it will be a linear function. So these are 3 kind of test functions which have been analyzed by researchers in the literatures. So you can say that for different models, for different scenarios, people propose different kind of models, and they have to do the analysis one by one. So this is some kind of ad hoc. So can we find a unified work, or can we find a unified model such that you can subsume all this kind of special case into a unified model. So this is our goal. So that's why we propose generalized group testing. So we want to understand the general principles under all these kind of group testing models. So first, the principle this is a principle we found that the more defective items or test contents, the higher probability of being positive, right? So this is a reasonable assumption that the more defective test contents, the higher probability of being positive. What does this mean? This translates into mathematics. It means that your testing function is a monotone function. So which means that if you have a larger number of defective items, your test result will, with a higher probability, will be positive. So you can say, based on this kind of definition, monotone test functions, we can further classify into noisy test functions, one-side lossless functions, and one-side lossless. So now the question is, if we under this kind of generalized group testing, under this kind of monotone test functions, we didn't make any other assumptions. So we only know that the test function is monotone. Can we still identify under this model? Can we still identify the subset of defective person or defective items? We still require that the probability error to be absolutely small. So I ask you to, instead of maybe precisely calculate the number of tests, could you still can you at least give me the scaling node? So first, is it possible to identify the defective set under this monotone test function? So the answer is yes. So we will use a non-adaptive group testing scheme. So for all non-adaptive group testing scheme, they can always be described by testing matrix. What is testing matrix? So we can use a matrix where the row corresponds to the number of tests. So for example, the first row corresponds to the first test. The last row corresponds to the last test. The column will correspond to the items. What is the value? The value will always be binary. So for instance, this value is 1, which this means this item, this third item, participate in the first test. And this value is 0, which means that this item didn't participate in the first test, right? So we can use this kind of binary matrix to describe this kind of non-adaptive group test. So our special test is called Bologna test. For Bologna test, each entry of this matrix is a IID Bologna random variable with parameter Q. So we will use this kind of non-adaptive group testing scheme. So now, in order to use this, we have to specify 2 parameters. So the first, what is the number of tests, which means what is the number of rows? Second, what is the parameter Q for the Bologna random variable Q? So we will specify this later. So suppose we already know the number of tests T and also know the parameter Q. After you have construct this kind of testing matrix, how can you do how can you identify the defective person? How? So in order to describe our decoding rules, I have to define 2 parameters. So these parameters actually the intuition is that the first the item I is non-defective. Suppose item I is non-defective and the probability of being positive. And this is the item I. If item I is defective, and the probability that that the test he participate is being positive, there are slightly difference. So how can we? Sorry, I have to. Sorry, I have to answer an important phone. So let me continue. So this is 2 parameters. Then how can I, after we have participate in large number of tests, how can I classify item I to be defective or non-defective? So mi denotes the number of tests which include item I, and mi superscript plus, which indicates the number of positive tests which include item I. So if I have a ratio, I compare the ratio of this the fraction of the positive test with this parameter. If it is larger than the parameter, then we can say the item is defective. It is smaller than this parameter, then we say it is non-negative, non-defective. So
okay.
Yeah, so we prove that if the number of tests equals to this number we can prove that the probability of error will be almost epsilon. So how can we prove this? We will prove that each item will participate in at least m tests. Sorry, this is a class alarm in my university. Second, we will prove that all items are correctly identified. Now you can say we already proposed a scheme which says that if you use this number of tests and you can with high probability correctly identify the subset, but still currently the characterization of this kind of number of tests is implicit. You can say it depends on some parameter which is delta Q. We haven't calculated. So I will not go into the details, but the high intuition is you have to use this kind of mean value theorem and also use some starter point approximation to get a bound to get a lower bound on this. So let me state our main result, which is a achievability, or also called as a upper bound. So in order to present our upper bound, we will introduce a sensitive parameter. So we call it %f. So you can say, since this parameter is a description of your function, so it mainly describes the shape of your monotone functions. So we already you can say this part corresponds to the Armoto term, and this part is the inverse of your slope. So the better you have larger slope, the better you have large sensitive parameters. So we can bound that for any monotone test functions, is sensitive parameters is always no larger than big O D. So, but sometimes this upper bound is pessimistic. For instance, for any omega which is between 0 and 1, and we consider this kind of test function, you can say that actually for this test functions, your sensitive parameter is only big O d to the power of omega. So since this omega, for instance, if this omega is half, you can say it is strictly smaller than this upper bound. So so I want to use this example to illustrate that our upper bound, even though this upper bound is universal, but most of the time it is pessimistic. So for the previous proposed scheme, we prove that first, the probability error is almost epsilon. Second, the number of tests is always smaller than this. Since we mainly focus on the scaling law, therefore you can the constant is quite larger, but it is okay if we focus on the scaling law. And the testing matrix parameters can be effectively approximated in polynomial time. So this what does this result imply? This implies that for any monotone test functions, the number of tests will always no larger than d squared log n log n. So no matter what kind of monotone test functions you have, your test number of tests required is always no larger than d to the power of 2 d squared log n. So in order to complement our achievability, we also derive the information theoretical lower bound. So information theoretical lower bound means that no matter what kind of strategies you use, the number of tests is always larger than some bound. So in order to introduce the information theoretical lower bound, let me define the concentration parameters. So this you can, even though this expression is a bit complicated, but this is a hypergeometry distribution. So you can say that's why you can say this is essentially the hypergeometry mean of this function. This is a hypergeometry distribution variance of this function. So our concentration parameter will define in this way. You optimize this parameter is representing the pool size. You can say the pool size is always between 1 and n-1. So we prove that this kind of concentration parameter is always larger than 1. Sorry. So the main result is for any non-adaptive group testing scheme, as far as you can identify the defective set with probability of almost with probability of error almost epsilon, the number of tests is always larger than this. You just compare these two. You can infer that the scaling law of the converse is always big O omega d log n over d. So now we have our upper bound, which is percent f d log n. We have a lower bound, which is little percent f d log n over d. So usually we in group testing we only care about the sparse region, right? So we only care about the sublinear region, sparse region. So under this kind of sparse region, d log n and d log n over d, these two are essentially are the same order. So this means your gap is mainly between percent f and little percent f. Since we call ourselves generalized group testing, so can our result recover the classical result in the classical setting? Because you can say for the classical testing functions, the scaling law is d log n. So we can recover the classical result because in the upper and lower bound, we can identify that the percent f and little percent f both equals to 1. Therefore, they are tight. Another is the threshold testing functions. We also prove that the number of tests is the upper bound and lower bound is tight. They are tight. And the final one is what we call the linear test functions. In this kind of linear test functions, we prove that the upper bound and both the upper bound and lower bound, they equal to the d squared log n. So this means that the linear test function is the worst case. It has the worst behavior because we say that no matter what kind of test function you have, as far as it is monotone, the number of tests is always no larger than d squared log n. So you can say linear test function is in this case is the worst kind of test functions. In general, except that for these three test functions, we already proved the tightness of the upper bound and lower bound. For general case, we prove even more tighter upper bound. So again, little percent f is the concentration parameters. This C parameter is a parameter we optimize with respect to this kind of concentration parameters. And for general monotone test functions, we can lower down the gap to big O, to big O, P mean, Q star, and mu chi star, and this. So the high level idea is we can prove that the sensitive parameter is always big O 1 over the variance of the concentration of the functions. So for low test function, based on this result, we find that for low test functions, our testing scheme is always order optimal. So for our paper, we also propose some open questions. So currently, we didn't provide a good upper bound on the P mean. So we simply upper bound it by 1. Can you derive a better upper bound? Right. So, and also currently for generalized group testings, we only studied non-adaptive testing scheme. So our questions arise is for adaptive algorithms, will it improve scaling law? I mean, we believe it shouldn't improve the scaling law as in the classical setting, but we still lack of a proof. And finally, all of our non-adaptive testing scheme requires a priority a precise knowledge of the number of testee, but how to estimate it is also unknown. So that's all for my presentation. So feel free to ask me any questions.
Thank you for your excited report. We maybe some have a questions about this report. I have a questions. We can combine your probabilistic approach with some large languages models maybe for improving some result. Are you tested something in this direction or not?
Yeah, I didn't compare with the combinatorial approach. So because you can say most of my approach are probabilistic approach. Yeah.
Okay, thank you very much. Edition, congrats. Please send me your presentation. I will share with our colleagues in Russia. Okay, in WeChat.
Okay.
Okay, thank you very much.